Dear learners, I am Gaurav Kumar Agrawal, Assistant Professor at UTD CSVT Bhilai. In today's session, we are advancing to the topic of foundation, that is deep foundation part 2. We will explore the pier foundations, coffer dams, caissons and their applications, load carrying capacity of piles, etc. By the end of this session, you will gain a deeper understanding of deep foundations and be prepared to apply this knowledge to the real world construction projects, ensuring stability and safety. We will discuss the following key points. First, pile load test. Second, group action in piles, then under-rimmed piles, then pier type deep foundations, then coffer dams and at last caissons. So, load carrying capacity of piles. The load carrying capacity of a pile can be determined by the following methods. First is dynamic formulae, second is static formulae, third is pile load test, fourth is penetration test. In the previous lecture, we have already discussed about dynamic and static formula. Now, let us understand the pile load test. The pile load test is a reliable method for determining the carrying capacity of a pile. It can be performed either on a working pile which forms part of the structure's foundation or on a test pile. The test load is applied using a calibrated jack placed over a rigid circular or square plate positioned on the head of a pile extending above the ground level. The jack's reaction is supported by a truss or platform which may carry gravity loads like sandbags, or the truss can be anchored to the ground using anchor piles. In some cases, under-rimmed piles or soil anchors may be used for this purpose. The load is applied in equal increments, usually about 1/5 of the estimated allowable loads. Settlements are recorded using 3 dial gauges with a sensitivity of 0.02 mm, symmetrically arranged over the test plate and attached to an independent datum bar. A remote controlled pumping unit may be used for the hydraulic jack. Each load increment is maintained until the settlement rate reduces to less than 0.02 mm per hour. The test continues until the ultimate load is reached. Typically, the test load is increased to 2.5 times the estimated allowable load or until a settlement equal to 1/10 of the pile diameter is observed, whichever happens first. The results are plotted as a load settlement curve. The ultimate load indicated when the curve approaches vertical. If the ultimate load cannot be determined from the curve, the allowable load is calculated as follows: half to 1/3 of the final load causing settlement equal to 10% of the pile diameter, 2/3 of the final load causing a total settlement of 12 mm, 2/3 of the final load causing a net settlement of 6 mm. Then the next is pile cap. When a column or pier is supported by a single pile, the column should be centrally placed on the pile. However, when the column or anchor load bearing structural component is supported by multiple piles, they must be connected with a rigid pile cap to evenly distribute the load across the individual pile. The pile cap is a rigid, deep, reinforced concrete slab that acts monolithically with the group of piles. The piles are arranged symmetrically around the column axis to ensure that the load is uniformly distributed among them. The pile cap is of uniform thickness and extends beyond the outer pile by 10 to 15 centimeter. The pile should be embedded at least 15 centimeter into the pile cap, and the cap's reinforcement should be placed at least 10 cm above the pile heads. The pile cap covers the entire area of the pile group and is considered to consist of a grid of rectangular beams. These beams are arranged based on the number of piles with their width matching the width of the piles. In order to prevent the outward splaying of the piles, secondary reinforcement should always be included. This reinforcement is placed at the bottom of the pile cap, running around the longitudinal reinforcement, projecting from the pile into the cap and bent at each pile head to change direction. Then the next is group action in piles. When several closely spaced piles are grouped together, the soil pressure developed as resistance tends to overlap. The bearing capacity of a pile group may not always equal to the sum of the individual pile capacities. Studies and tests show that for groups of friction piles, particularly in clay, the total bearing value of the group, that is Qg, may be less than the product of the friction bearing value of the individual pile, that is Qf, multiplied by the number of piles n in the group. However, no such reduction occurs for end bearing piles. For piles that rely on both end bearing and friction, only the load bearing capacity related to friction is reduced. To estimate the bearing capacity of a group of friction piles, the product of N and Qf is multiplied by a reduction factor known as the efficiency of the pile group, that is eta g. The formula is given as Qg is equal to N multiplied by Qf multiplied by eta g, where Qg is equal to load carried by the group of friction piles and Qf is equal to load carried by each friction piles, and N is equal to number of piles, where eta g is equal to efficiency of the pile group. The efficiency of the pile group is influenced by factors such as pile properties like length, diameter, material, pile spacing, the total number of piles in a row and the number of rows. Various methods are available for determining the efficiency of the pile groups, with Feld's rule being one commonly used approach. So, what is Feld's rule? According to this rule, the capacity of each pile is reduced by 1/16 due to the influence of the nearest pile in each diagonal or straight row. This reduction applies to the pile in question based on its position within the group. Then the next is under-rimmed piles. Under-rimmed piles are bored cast in situ concrete piles with one or more bulbs forming by enlarging the borehole using an under-rimming tool. These piles are useful in various soil conditions, particularly where foundations need to reach a certain depth to avoid seasonal moisture changes such as in expensive or black cotton soils. They are also effective in providing adequate capacities for downward, upward or lateral loads, and for situations where foundations need to be placed below score level. The construction of under-rimmed piles involves several stages with the necessary equipment including an auger boring guide, spiral auger with extension rods, under-rimmer with a soil bucket and a concreting funnel. A portable tripod hoist with a winch is typically required for piles longer than 4 to 5 meters or with diameters larger than 37.5 centimeter. Under-rimmed piles can have one bulb known as a single under-rimmed pile or multiple bulbs known as multiple under-rimmed pile. The bulb's diameter is usually taken as 2.5 times the diameter of the pile stem, but may vary between 2 to 3 times the stem diameter depending on the design and construction requirements. When forming more than one bulb, the borehole is first excavated to the depth of the top bulb and then under rimming is carried out. This process continues until the desired depth is reached. In expensive soils, the minimum pile length should be 3.5 meters to minimize ground movements. For shallower depths or other poor soils, the length be reduced depending on the load requirements, but the piles must extend at least 50 centimeter into the stable soil. Pile length can be increased to handle higher loads. Manually bored piles typically range in diameter from 20 centimeter to 37.5 centimeter. The spacing of piles depends on the nature of the ground, the pile type, and how the pile transfers load to the soil. The center to center spacing for under rimmed piles is generally at least 2 times the under rimmed diameter, denoted by du. For a spacing of 1.5 du, a 10% reduction is in the load carrying capacity of the pile is applied. The bearing capacity of the pile group is taken as the number of piles multiplied by the bearing capacity of an individual pile, and an average spacing should be used when adjacent piles have different diameters. The maximum spacing should generally not exceed 2.5 meters to avoid the need for heavy capping beams. In buildings, piles should be placed under all walls junction to avoid point loads on the beams, and intermediate piles should be positioned so that the door openings fall between the piles when possible. For double and multi-rimmed piles less than 30 centimeter in diameter, the vertical spacing between bulbs should be 1.5 du. For piles of 30 centimeter or more, this spacing can be reduced to 1.25 du. The upper bulb should not be placed too close to the surface with a minimum desired depth of 1.5 meters or 2 du, whichever is greater. Under rimmed piles are typically reinforced with 10 to 12 mm diameter longitudinal bars and 6 mm rings. A clear cover of 4 centimeter is provided. These piles are connected by a reinforced concrete beam known as the capping or grade beam. In expensive soils, the grade beam is kept above the ground with an 8 to 10 centimeter air gap to accommodate soil expansion. In non-expensive soils, mass concrete of 8 to 10 centimeter thickness is placed between the ground and the beam's underside. Under rimmed piles are suitable for sustaining large lateral loads, making them ideal for tower footings, retaining walls and abutments. They are also used in factory buildings, machine foundations and transmission line towers and poles, particularly in expensive soils like black cotton soils. The piles anchors the structure at a depth where soil movements due to seasonal changes are minimal. The next type of foundation is pier type deep foundations. Pier foundations are a type of deep foundation used to transfer heavy loads from structures to deeper stable soil or rock layers. Piers are generally large cylindrical columns constructed to support and transfers the load to firm strata below the surface. These foundations are typically used in situations where shallow foundations like footings are not suitable due to weak or highly compressible soils near the surface. Then what are the various types of pier foundations? First is drilled pier foundation. A deep hole is drilled into the ground and then concrete is poured with or without a steel reinforcement cage to construct drilled pier. It transfers load to the deeper, stable soil or bedrock through end bearing or skin friction. It is ideal for supporting heavy structures such as bridges, towers or multi-story building in weak or loose soil. Then the next is concrete pier foundation. It is precast or cast in situ cylindrical concrete piers and are installed into the ground. It can rely on end bearing or a combination of skin friction and end bearing. It is frequently used for buildings, retaining walls and other types of heavy structures. Then the next is caisson open pier foundations. It is a watertight chamber or box is lowered into the water or mud and then soil or mud is excavated from within, after which concrete is poured. It primarily uses end bearing to transfer the load to firm rock layers. It is commonly used for bridges, docks and other types of marine structures. Then what are the various properties of pier foundations? First is depth. Pier foundations are typically deeper than the shallower foundations and may extend to several meters below the surface. Second is load capacity. They can support very high loads, making them suitable for tall or heavy structures. Third is cost. Generally more expensive than shallow foundations due to the complexity of the construction, particularly in drilled or caisson pier. Fourth is flexibility. It can be designed to handle both the vertical and lateral loads, offering flexibility in foundation design. Then what are the various applications of the pier foundations? First is bridges and overpasses. Due to their ability to reach deep stable layers, piers are commonly used in the construction of the bridges. Second is towers and skyscrapers. Tall buildings with heavy loads often require a deep foundations like piers to ensure stability. Third is marine structures. Structures like piers and docks which are built in the water or near shorelines rely on deep pier foundations for its stability. Fourth is retaining walls. It is used to support retaining walls in areas with unstable or weak surface soils. Then what are the various advantages of pier foundations? First is deep stability. It can bypass weak surface layers to reach stable strata deep underground. Second is high load capacity. It is suitable for heavy and high rise structures. Third is lateral load resistance. Provides good resistance to lateral forces such as winds and seismic activities. Then what are the various disadvantages of pier foundations? First is complex construction. It requires specialized equipment and skilled layer for drilling and pouring. Second is cost. It is more expensive than shallow foundations due to deeper excavation and material uses. Third is time consuming. The construction process can be slow, particularly for drilled and caisson piers. Now the next is cofferdams. A cofferdam is a temporary structure designed to enclose a specific work area in water bodies such as rivers, lakes or oceans to keep water out during construction activities. The primary function of a cofferdam is to create a dry working environment by preventing water from entering the enclosed area, making it possible to build foundations or other underwater structures. Even with a cofferdam in place, some water may leak through the walls and the foundations, so continuous pumping is often required throughout the construction process to maintain a dry workspace. Coffer dams can be constructed from various materials such as earth, timber, steel sheet piles or combinations of these materials depending on the specific requirements of the project. These are several types of coffer dam, is suitable for different conditions and project requirements. Some common types include: first is cantilever sheet pile coffer dam. This type of coffer dam consists of vertical sheet piles driven into the ground and left unsupported by any type of bracings. They are most suitable for projects with small heights. While simple in design, cantilever sheet pile coffer dams are more vulnerable to water leakage and flood damage due to their lack of bracing and support. They are effective in situations where the water level is not high and the water pressure is manageable. Then the next is braced coffer dam. Braced coffer dams involves sheet piles supported by internal bracing systems such as struts or wells. These bracing elements provide additional stability, making braced coffer dams more suitable for small to moderate heights. The bracing system helps resist water pressure, reducing leakage and the risk of collapse, which makes them more economical and widely used in shallow to moderately deep water conditions. Then the next is embankment protected coffer dam. Constructed using earth material, embankment coffer dams do not have a specific height limitations, making them versatile for various project scales. However, they occupy a large base area, so they are generally used for larger excavation areas where ample space is available. Earth embankment coffer dams provide a natural barrier, but may require extensive material and are more susceptible to erosion and failure if not properly maintained. Then the next is double wall coffer dam. This type of coffer dam consists of two parallel walls of sheet piles or timber that are filled with earth or other materials for additional stability. Double wall coffer dams are suitable for moderate heights and offer better protection against water leakage compared to single wall systems. The space between the walls provides extra resistance to the water pressure, making them reliable for projects requiring a higher level of water exclusion. Cellular coffer dam. Cellular coffer dams are constructed using large cells formed from the sheeting piling. These cells are typically circular or another curved shape and are filled with materials such as rock, gravel or sand to create a stable structure. Each cell acts as a vertical cylinder with dimensions ranging from 9 to 12 meters in lateral size. Cellular coffer dams are highly effective for moderate to large height requirements and can withstand significant water pressure. They are commonly used in situations where high water levels or strong currents are present, such as in deep water or tidal areas. Then the next is caissons, also known as well foundations. Caissons, often referred to as well foundations, are large watertight structures used for underwater construction, primarily in bridge and pier foundations. The term caisson is derived from French word caisse, meaning chest or box. The structure resembles a box, whether rectangular or circular, that is sunk into the ground and water to reach a stable bearing stratum at the desired depth. Caissons are used when shallow foundations cannot provide the required stability due to water, deep soil layers or other unfavorable conditions. Caissons are classified into three main types: based on their structural design and application. First is box caisson, second is open caissons or wells, third is pneumatic caisson. Each type of caisson is designed to suit specific environmental and structural conditions with advantages and limitations that determine its appropriateness for various construction scenarios. First is box foundation or box caissons. Box caissons are large prefabricated structures open at the top and closed at the bottom. They are constructed on land and then floated to the construction site, where they are sunk into the position, typically made from materials such as timber, reinforced concrete or steel. Box caissons are filled with sand, gravel or other appropriate materials to provide weight and stability during sinking. These caissons are typically used in situations where the bearing stratum is at shallow depth and the structural loads are relatively light. The construction of box caissons begins by preparing the site, usually by dredging to create a level surface. Once the area is ready, the prefabricated caissons is floated to the site and sunk by gradually filling it with ballast materials like sand or gravel. After the caisson reaches the desired depth, it is sealed at the top to form a stable permanent foundation. Box caissons are commonly employed in the construction of breakwaters, sea walls and similar maritime structures. Their main advantages lies in their simplicity and ease of construction, particularly in shallow water where deep excavation is not required. Then the next is open caissons, that is well foundations. Open caissons, also known as well foundations, are widely used in bridge and building construction, especially in regions where foundation must reach deeper layers of soil to avoid issues like score or inadequate bearing capacity. Unlike box caisson, open caissons are open at the top and bottom. The caisson is sunk into the ground and excavation is performed inside the caisson, progressively deepened it until it reaches the required depth. The open caisson is generally made of materials like timber, reinforced concrete, metal or masonry. In India, well excavation or foundations are the most common deep foundation system for bridges due to their efficiency and stability. Whenever the foundation needs to reach depths beyond 5 to 7 meters, open excavation becomes impractical due to the cost, time and safety concerns. The process of heavy timbering and side slope management required in traditional excavation can be avoided with open caissons, making them more economical and faster to install. The sinking of an open caisson involves excavating material from inside the caisson while its own weight causes it to sink into the ground. This method allows for controlled sinking, especially in deep water or challenging soil conditions. The excavated water or material is often removed using a dredging pump and the caisson sinks. More material is excavated until the foundation reaches the necessary depth. Then what are the various shapes of well foundations? Well foundations come in various shapes, each require with the specific advantages depending on the project requirements. The most common types of well shapes include: first, single circular wells. These provide symmetrical distribution of forces and are often used for single pier foundations. Second is rectangular wells. These are suitable for long, narrow structures like bridge piers. Third is twin circular wells, ideal for cases where large structures require multiple support points. Fourth is dumbbell shaped wells. This shape offers enhanced resistance to lateral forces and is often used for complex or high load structures. Fifth is double D shaped wells, a more specialized design used for design or large heavy loads and challenging conditions. Then what are the various components of a well foundations? Well foundations consist of several key components, each serving a specific purpose in the overall structural integrity. First is well curve and cutting edges. These are the bottommost part of the well foundation that help in cutting through the soil as the caisson sinks. Second is steining, the cylindrical or the rectangular walls of the well that provides structural stability during sinking. Third is bottom plug, a concrete seal placed at the bottom of the well after reaching the desired depth, securing the foundation. Fourth is well cap, the top closure of the well which serves as the load transfer mechanism between the superstructure and the foundation. Open caissons are widely preferred for deep foundations due to their stability, ease of construction and the ability to reach greater depths without excessive excavation. However, in cases where soil conditions or water pressures are extreme, pneumatic caissons may be more suitable. Then the third type is pneumatic caissons. Pneumatic caissons are similar in design to open caissons, with the primary difference being that the compressed air is used to keep water out of the working chamber. This type of caisson is typically closed at the top and open at the bottom, allowing workers to excavate soil under dry condition, even underwater. The air pressure inside the caisson is maintained at level just higher than the external water pressure to prevent water from entering the working chamber. Pneumatic caissons are used in cases where it is essential to carry out excavations in dry conditions, such as in deep water construction or in environments with high water tables. The controlled dry environment ensures better quality control of the foundation work, including more precise construction, concrete placement and easier handling of obstructions like boulders or tree roots. Then what are the various applications of caissons? Caissons are used in a variety of construction projects, particularly in areas where shallow foundations are not feasible due to soil conditions, water presence or other environmental factors. The main applications include: first, in bridge foundations. Caissons are commonly used to support piers in river beds or other water bodies where deep foundations are required. Second is building foundation. In areas with poor soil conditions, caissons provide the necessary stability for large structures. Third is marine structures. Caissons are frequently employed in the construction of docks, breakwaters and sea walls, providing stable foundations in challenging environment. Fourth is offshore structures. For oil rigs, wind turbines and other offshore facilities, caissons offer reliable foundation system that can withstand the harsh marine environment. Dear learners, we have reached the end of today's session. I hope you found it informative and engaging. Thank you for your attention. See you in the next class. Thank you.